Now, we saw how when we dissolve acids in a solution, they form H3O plus ions. And we also know how to compare one acid with another. So, for example, when we dissolve hydrochloric acid in water, we form Cl minus and H3O plus. And we know it's an acid because it dissociates to give us H plus, which is donated to water to form H3O plus, hydronium ion. We also learned how to compare the acids, and here are different acid strengths. We already saw this. Well, we are comparing which acid is stronger against another by comparing how much one acid dissociates compared to the other. And we actually assign equilibrium values to those dissociations, but we'll not go deep into that. But one way to compare how strongly our solution is acidic is by looking at this reaction and seeing that it's this component which makes the solution acidic. And if we know the concentration of this species, hydronium ion, in solution, then we can compare one solution with the other and classify one as being more acidic than the other depending on which one has greater hydronium ion concentration. And that's exactly what we will do now. So we have established something known as the pH scale, which lets us find out how strongly acidic a solution is or how strongly basic it is. The pH scale basically takes the concentration of H3O plus ions and takes the negative logarithms of it. There is a special key on your calculator, your scientific calculator, which says log. You take the log of a certain number and you multiply it by -1, or just take the negative of it, and you will get the pH value. The pH values in a solution, in an aqueous solution, range from 0 to 14. If you have a value of 0 for some H3O plus concentration, then you have a very, very acidic solution. If you have a value of 14, on the other hand, you have a very basic solution. So it's on a scale of 0 to 14. Let's look at why it could be very acidic and why it could be very basic. If the concentration of H3O plus is high, the solution will be very acidic, and the value of pH will be closer towards 0 than 14. Now, why would it be very acidic and not very basic? Because it can only be one or the other. You cannot have a very high H3O plus concentration and a very high OH minus concentration. You can either have a very high H3O plus concentration and very low OH minus concentration, or very high OH minus concentration and very low H3O plus concentration. Why is that the case? Remember, water has its own dissociation. We express that as Kw equals H3O plus concentration times OH minus concentration. What does this mean? It means that if I was to come along and add some H3O plus here by adding some acid like HCl, which will give you H plus, which gets picked up by water to form H3O plus. So if the concentration of this goes up, the concentration of OH minus must come down. Only then would the product of these two still equal to the same number, which remains constant, which is here actually 1.0 times 10 to the negative 14. So increasing the acid concentration invariably decreases the base concentration in water. Similarly, if I was to add NaOH in water, then this concentration, hydroxide ion concentration, will go up. And if this goes up, for the ion product constant for water to remain the same, H3O plus concentration must come down. And so you could either have a strongly acidic solution or a strongly basic solution, either, but not both at the same time, because of the ion product constant for water, which is 1.0 times 10 to the negative 14. If you have both of them equal to each other, then you have equal amounts of the acid and the base, and in that situation we come back to the original situation, which is given here, where you have a neutral solution where there is no excess of the acid or the base, and the pH value for that situation will be right in the middle between 0 and 14, which happens to be pH of 7. You may have heard that a pH of 7 is indicative of a neutral solution. A pH less than 7 indicates acidic solution, and a pH greater than 7 indicates a basic solution. We measure pH many ways, but in the lab we use one specific instrument called pH meter, which is just an electrode which has electrical properties which senses the proportion of H3O plus ions in the solution and then assigns a pH value to the solution. It gives you a digital readout with the pH value. Then another way of finding the pH of a solution is by using indicator strips, which are just dyes that change color depending on what the pH of the solution is. Some dyes will turn red if the pH is between 1 and 2, other will turn brown if it's between 2 and 3, and so on. So by using various combination of dyes, we can figure out what the pH of the solution is. So let's do a calculation now where we find the pH of a solution. How do we calculate the pH of a solution when either the H3O plus or OH minus concentration is known? We calculate that by these two facts. One, pH equals negative log of H3O plus concentration, and other fact given here as the product of H3O plus concentration times OH minus concentration equals this value. So suppose you are given OH minus concentration in a problem, you can always find the H3O plus concentration by dividing this number with the OH minus concentration, giving you the H3O plus concentration, and then plugging in the H3O plus concentration here to give you the pH. You will find that pH values are documented for just about any solution, even in a medical environment. pH is very, very important, the pH of solutions and so on. So if you have a 1.0 times 10 to the negative 4 molar HCl solution, what is the pH of that solution? What does this mean? It means that when we dissolve HCl in water, it produces exactly 1.0 times 10 to the negative 4 molar H plus, because for every 1 mole of HCl we produce 1 mole of H plus. And so when we talk about H plus, it's the same thing as H3O plus, because H plus gets picked up by H3O plus, by H2O to produce H3O plus. So we have 1.0 times 10 to the negative 4 molar H3O plus. When we take the negative log of that, we get 4.00. It's a fairly acidic solution. It's not very acidic, but it's fairly acidic. Calculating H3O plus from pH now, the other way around. So if this is the equation for finding the pH, the inverse equation, if you know your math, is to raise both sides to the power of 10, and the log function and the power of 10 function are inverses of each other, they will cancel out. And so on the right here we will just end up with H3O plus concentration, while here we will have 10 raised to negative pH when we divide both sides by this negative term. So if I have the pH such as pH equals 6.00, I would then use that, the negative of that, as an exponent raised over the base 10. So 10 raised to negative 6.00. When you do that in your calculator, you will get H3O plus concentration as 1.0 times 10 to the negative 6 molar. Now here is one other fact. When you are converting between pH and H3O plus concentration, what happens to the sig figs? Whenever you take the pH of your acidic solution and you have the H3O plus concentration, for example, if the H3O plus concentration is 1.0 times 10 to the negative 6 molar, how many sig figs do you see here? All the sig figs reside in the coefficient, and there are two sig figs. And when you convert this number to the pH, the sig figs, the two sig figs here show up as 2 digits after the decimal point here. So altogether there are altogether there are 3 sig figs in 6.00, but the two sig figs showed up after the decimal point. And when you convert it back to your original H3O plus concentration like we did in this problem, only those two sig figs should be the total number of sig figs in your coefficient here. So remember that fact when you interconvert between pH and H3O plus concentration. Now here we have to take one more step. We are given KOH solution, which is 1.0 times 10 to the negative 3 molar. When you dissolve this in water, you have K plus ions and OH minus ions. So we have fairly high OH minus concentration, and so we should have fairly low H3O plus concentration for water to maintain its ion product. So what is the pH of this solution? First we have the OH minus concentration. We will find the H3O plus concentration using this equation. We will divide 1.0 times 10 to the negative 14 molar by the OH minus concentration we have there, and that will give us our H3O plus concentration. And once we have the H3O plus concentration, we can plug it in this equation, and just like the previous problems, we will find the pH. So our H3O plus concentration is 1.0 times 10 to the negative 11 molar. Be careful when you do math with this kind of scientific notation numbers, because you need to put these numbers in parentheses in your calculator for them to give you the right answer. Parenthesis here and parenthesis, closing parenthesis here. Similarly, opening parenthesis here and closing parenthesis here. And you get H3O plus concentration here, which when you plug in the pH equation, you get your pH equals to 11.00. By the way, what does the P in the pH stand for? The pH scale was developed by a German chemist, and it stands for potens, P-O-T-E-N-Z, potens of H, or potens also means in English translated, it means power of hydrogen ions. Right. Here is another problem. Calculate OH minus from pH. OH minus concentration from pH. So now we are going the other way. What will we do? We will find the H3O plus concentration from pH using that equation, where we take the negative of the pH and raise it over 10, and we get H3O plus concentration as 1.0 times 10 to the negative 5 molar. And then using the fact that the water ion product is 1.0 times 10 to the negative 14, we divide the water ion product by the H3O plus concentration we just found, and we get the OH minus concentration given here. So here is a pH scale of different solutions. Notice that neutral water right in the center is given a pH of 7. Blood has a pH of 7.4. Saliva is fairly acidic with a pH of 6.5. That's why saliva can kill a lot of germs, and orally it's not very likely to be infected as much as through other means, as in being directly infected through blood. Urine is also acidic. Coffee, tomatoes, all plants and vegetables are fairly acidic. Vinegar, as we know, is acidic, and so is Coke. Lemon contains citric acid, and stomach has very highly acidic solution to digest proteins. And notice this way, compare this with hydrochloric acid. Hydrochloric acid, pure hydrochloric acid, has a very, very low pH. On the other hand, on the other side, seawater is fairly slightly basic. Baking soda, if you know, is basic. Morse, Great Sea Salt Lake is basic. Ammonia is basic, as we know. Soda ash, oven cleaners, and finally sodium hydroxide. They are very basic. Right, so molarity and pH. And here are some common values for pH, as well as what concentration H3O plus or OH minus would be in the case of different pHs. So here pH 0 means you see this 0 here show up up here as an exponent. Similarly, this 1 shows up with as a negative exponent here, and the 2, and so on. So this is how, when the pH is going down, the concentration is actually increasing. Concentration of H3O plus, that is. And here with a pH of 14, what we have here is the OH minus concentration. Very pH of 14 means the OH minus concentration should be very high, but as we go closer towards neutrality, the OH minus concentration drops, and at pH of 7, the H3O plus concentration and the OH minus concentration are the same. Okay. So what's the importance of pH and pH control? We find pH in agriculture. Certain crops grow in acidic soil, certain crops grow in basic soil. Having optimum pH is necessary for healthy crops. Physiology, your blood pH, if it shifts not just by 1 point as it says here, but even by 0.1 or 0.2, that could be fatal. pH of blood is 7.4, you don't want it to be 7.5 or 7.6, for example. We know acid rain, whenever we release pollutants in the air, they combine with, for example, sulfur dioxide, sulfur trioxide, produce sulfuric acid, acid rain, and it can cause problems with sea life or aquatic life in general. The sewage treatment plants contain very acidic situations to optimally purify water, for example, and even in industry, a lot of chemical reactions depend. In fact, I would say most chemical reactions monitor the pH at which those reactions are conducted. So controlling the pH of a solution and being aware of what it is vital for practicing safe chemistry as well as productive chemistry.